эта штука уже включена, да? Может быть, хорошо. Не включена. Ну, так. Так, ну хорошо. Well, since we're being recorded, I have to speak English. So, if you want to be on the mailing list for this seminar, please put your name and your email, and I'll include you. Okay. Well, the name of the course is localization and rational homotopy theory. Okay, so if there are parts of the board which are not visible, please let me know, because otherwise there's no way for me to determine which parts are all right. Okay, so rational homotopy theory. Well, my email is Gorinov .hsc RU Alexei Gorinov. No surprises there, just in case. We will meet every week on Wednesday, 4:20 p.m. 7 something. p.m. and there will probably be an exam at the end and or problem sheets. I don't remember exactly what the arrangements are. Basically, whatever it says in the course book is true, and I don't remember. Any questions so far? Depending on the wishes of the participants, we may focus on either localization in general or rational homotopy theory, which is a particular case of localization. Okay, so if you wish to participate but the time is inconvenient or the day is inconvenient, please let me know, and then we may or may not be able to reschedule the class. Yes. for well, for technical reasons, it's another day is possible, but starting earlier than 4 would be inconvenient. Well, then it must be true. But well, one thing I want to say straight away: we may there might be talks by you, the participants, and those will be an alternative option, an alternative route to get a mark at the end. So let's think about that when we've more or less decided what exactly we want to do. Any more questions? Okay, so let me start by explaining what localization is. It's a very simple categorical construction, and basically some examples of this construction are already familiar since primary school. We'll cover those. So suppose we have a category and a class of morphisms such that the class is closed under composition, and it contains all identity morphisms. Then C with W inverted, CW minus 1 is the initial object in more precisely, let me put a C here. So I don't want to consider just the category C with W to the minus 1. I want to consider a functor from C to this category, and this functor will be the initial object in let me let me put it this way. It's the initial object in the category of functors from C to some other category, such that the functor takes all elements of W to isomorphisms. Now, we will shortly see that this thing exists by general nonsense. But what does it have to do with primary school? Let's have a look at a few examples. Well, first of all, I can take a commutative ring with identity. And I can consider it as a category with one object. And then I can take any multiplicative subset of of R, which means is closed under under the product, and it contains 1. And then we get something which is familiar from commutative algebra, the usual localization of a ring with respect to a multiplicative subset. Now, if this is not elementary enough, by the way, is this part of the board okay? Good. For example, we can take R equals Z, and W equal Z minus 0. And then the resulting category will be Q, meaning it will be the category again with one object, and the category with one object is a monoid, just by definition, and this monoid will be isomorphic to Q with its usual product. Does this make any sense? Now, when I was in the first form, they taught me that you cannot divide by 0. You're not allowed to divide by 0, and this annoyed me. But actually, why? If a multiplicative subset of R contains 0 or a 0 divisor, the localized ring collapses. It becomes a ring with one element. And well, it's a ring, yes, but not particularly interesting. So this illustrates the following fact: if we take an arbitrary category it's usually very difficult to tell whether or not the localized category is equivalent to a category with just one object and just one morphism. And by the way, remark just to illustrate that the problem is in general difficult. Let's consider finite categories, meaning all morphism sets are finite, and the set of objects is again finite. Then it's not possible to tell whether or not the localized category collapses. Which is basically straightforward if we remind ourselves that for semigroups none of the questions is none of the natural questions is algorithmically solvable. Anyway, we will not be very much interested in finite categories, but just as an example. Okay. Now, any questions so far? Okay. Well, instead of a category with one object, we can consider categories with many objects. So another example. In commutative algebra, we also know how to localize modules, not just rings modules. So we consider again the category. We consider the category of modules this time instead of just one object, which is a ring, and we again take a multiplicative subset of the ring, and we consider morphisms in C, which are multiplication, which are given by multiplication by elements of S. And we get the localized category, which is the usual localization from commutative algebra. In commutative algebra, we know how to localize not just rings but modules, and moreover, we know that localization is a functor. And basically, this is another example which is probably familiar to some of you. But we in this course or seminar we will mainly be interested in examples which come from topology. So let's give a few topological examples. let's consider the category of topological spaces, and let's consider the class of weak equivalences or just equivalences as W. Well, weak equivalences are maps which induce isomorphisms of all homotopy groups, and of pi naught, which is not a group, as I said, but anyway. And just equivalences are homotopy equivalences. Both versions make sense. If we invert weak equivalences or just equivalences, we get the homotopy category of topological spaces. And this category is quite complicated. So our goal, not just our goal, but one of the main goals of topology in general is to understand as much as possible about this complicated category, or failing that, to understand at least something. And this is so interesting. Very interesting. Very interesting, but also very complicated. And the rational homotopy theory has the advantage that it's also interesting, as we'll see in a minute, but not quite as complicated as the true homotopy category of topological spaces. So the rational homotopy category can be seen as an approximation of sorts to the true homotopy category. Well, to give another example, to give another example, we could take some functor from top to somewhere else. Just some category, and we take we then take the preimage of the isomorphisms, meaning we take all maps which go to isomorphisms in D. For example, if f is pi lower star, get the previous example. If f is integral homology, and we consider simply connected spaces, then we also get the previous example. If f is the integral homology, but we consider arbitrary spaces not necessarily simply connected, we get something complicated. If so this is same as this is the same as the previous example if we consider simply connected and connected spaces. We could take f equal homology mod p, where p is a prime number. Then we get something which is called p completion. Which is another side of so this category, how top, the one that's complicated. It has several avatars. In this seminar, we will mainly study the most the easiest one of those, which happens when we replace the coefficient ring here with Q. But we also have other avatars, and in particular, there's a parallel theory for every prime p, and we will not go into detail about this theory, but it exists. Okay, now the example we will mainly be interested in this course we will mainly be interested in the following example. We consider, again, spaces which are connected and simply connected, and we want to consider maps which induce isomorphisms of the homotopy groups tensor Q, which which is the same as requiring that F induces an isomorphism of H lower star tensor Q. Does this make sense? And now, here is one of the theorems that we will prove. There is an equivalence between the localized category in this example and the category of commutative differential graded algebras over Q. So CDJ means the category of commutative differential graded algebras greater than or equal 0 means we consider only non-negatively graded algebras. H1 equals 0, no, H1 equal Q means, H naught equal Q means H naught is equal Q. H1 equals 0 means H1 equals 0. And those categories, those algebras are all over Q. Does the statement of the theorem make any sense? So, in other words, we were able to algebraize spaces up to if we consider spaces up to rational equivalence, which is what it says here. Now, what happens if we do not require pi 1 trivial? Everything gets complicated, and there are several inequivalent ways to define the localization, meaning the class of morphisms which we try to invert in this case. Let's worry about this later. The simply connected case is interesting enough. Moreover, and we will also prove this. elements of the localized category can be thought of as genuine spaces. Okay, so let's see what I wrote here. This C with W inverted is the same as this one. Nothing changes. How is the homotypic category in the same sense as here? We take something, we invert homotypic equivalences. This time, genuine homotypic equivalences. But what is top Q? Top Q. Top Q with, again, assuming pi 1 equals 0. It's a full subcategory of just top. And a space is in this category if and only if its homotypic groups, which are just abelian groups in general, in fact, turn out to be Q vector spaces. An abelian group has just one structure of a Q, at most one structure of a Q vector space. So it does make sense to ask whether or not a given group is a Q vector space. Well, basically, an abelian group has a unique structure of a Q vector space if and only if this group is torsion-free and divisible. Okay. So the localized category is in fact the category up to equivalence, the category of Q local spaces, and this Q local is this condition. Up to homotypic equivalence. And this phenomenon is a particular case of what is called the Bousfield or Bousfield or Bousfield localization. Don't know how to pronounce the name. We'll talk about that. Anyway, the summary. This localized category has three incarnations. Number one, the one that comes from the definition. Number two, the one that comes from algebra. And number three, the category of some spaces, which is a full subcategory of topological spaces, where we invert genuine weak equivalences. Okay, any questions so far? If I'm saying something that doesn't make sense or you don't understand, please let me know. In fact, those two things may be correlated. Anyway, any questions? Пока реклама. Yes, so okay, now I had there are two things which I want to talk about. Well, firstly, let me talk about applications of rational homotopy theory. But before I do this, I will need to mention minimal models. We will I will define some algebraic object, and then we will see how it applies to topology. Now, I want to define a minimal CDJ. CDJ, commutative differential graded algebra. Does this expression make some sense, any sense, or none whatsoever? Good, good. So suppose we have a CDJ. I want to yes, I want to define a minimal CDJ. Now, I've written something on the board. What does it mean? Well, first, I've written the letter lambda. What does lambda mean? Well, lambda means free commutative graded algebra. What does commutative graded mean? Hopefully by now most people have realized that commutative is commutative in the graded sense. Meaning, when we have A and B, then A times B is not quite the same as B times A. It's B times A times minus 1 to the degree A times degree B, and then BA. So it's commutative, yes, but in a graded sense. Okay, free. What does it mean, free? Does everyone understand what the word free means? Well, by general nonsense, free is left adjoint of forgetful. But what does it mean in practice? Well, in practice, this means let me choose some generators of the graded. Well, let me choose some generators. So each x alpha is a graded variable. In particular, it has some degree. Now we have two cases. The degree can be even or it can be odd. Let me first consider what happens when there is just one variable. If the degree, but this variable has a degree. If the degree is even, I just take the polynomial algebra. If the degree is odd, then as a vector space, I just take the direct sum of q in degree 0, another q in degree x, and the multiplication is the same as the multiplication in the cohomology of the sphere of dimension degree x. Does this make sense? Now, once I have the free algebra generated by one variable, and I can generate free algebras using an arbitrary number of variables by taking just the tensor product. And so we have explained the words free graded commutative algebra. Well, example. Cohomology of S to n minus 1 with Q coefficients is free. The cohomology of CP infinity, again with Q coefficients, is free. And later on, today, we'll see Eilenbach-MacLane spaces, and the cohomology of those rationally is also free. Okay. Now, I want to say something about the differential. Well, the differential has to satisfy the following the following condition. For each variable alpha, x alpha, the differential must be expressible through x betas with beta less than alpha. And there is just one other condition which I call indecomposability. The differential must induce the zero differential on the indecomposables of the algebra. We'll talk about that. Basically, if I have two variables, x1 and x2, and d of x1, d of x2 is x1, then I get a redundant tensor product, tensor factor in this algebra. I don't want it. So indecomposability is what is related to the minimal condition. Okay. Now we are ready to say two things. Well, firstly, well, this is a technical statement, but we will need it to describe applications in a minute. Firstly, every commutative differential graded algebra with h naught equal q, I do not need to assume that the h1 is 0. Every CDJ with this condition has a minimal model, meaning there is a minimal algebra M, which maps into A, and this map is a quasi-isomorphism of algebras. By the way, okay, here what I said was some category is equivalent to some other category, but I forgot to mention that this other category needs to be localized as well. In other words, the homotypic, it's hard to expect the homotypic category to be equivalent to just some category which is formed by some sets with some structure. Why? Well, because the homotypic category of topological spaces is not concrete. Does anyone know what this means? The homotypic category of topological spaces is not concrete. Yes, exactly. There is no faithful functor intersets. Okay. Now, so if we take this category, we need to quotient out quasi-isomorphisms. Okay. Now, a few words about applications. Application number one, the ranks of the homotypic groups. As many of you probably know, the homotypic groups are difficult to calculate. For example, it's very hard to calculate even the homotypic groups of the two-dimensional sphere. And same applies to the other spheres and basically to almost every space. But the ranks of the homotypic groups are relatively easy to calculate. We know that if we have a simply connected space of finite type, which means it's a homotype equivalent to CW convex with finitely many cells in each dimension, then the homotypic groups are finitely generated abelian. Great. But so this means each of those is isomorphic to Z plus some torsion. Torsion is very difficult, but the free component is easy. And the ranks of the homotypic groups are calculated as follows. I take a space X. I assume that pi1 is a trivial. Then I construct something which we haven't defined yet, but we will. It doesn't matter what it is. What matters is it's a CDGA, a commutative differential graded algebra. And starting from it, we construct its minimal model. Then, by I, the rank of by I of x is the same as the number of generators of degree I. Well, for example, let's take x equal an odd-dimensional sphere. Then the minimal model is is just lambda of x with 0 differential and x of degree 2n minus 1. And so we conclude that all homotopy groups of an odd-dimensional sphere are torsion. Except the group pi n minus 1. Okay, which is something that certainly can be proved in several different ways, but here we are. What happens when the sphere is even dimensional? Is it true that all homotopy groups of S2n are torsion except in dimension 2n? No. Well, let's see why. Okay, but let's see what happens. Well, first, I need to account for the group pi to n, which is still there, and so I have an x. And then what happens if I generate a free commutative algebra using x? I get cohomology in all degrees which are multiples of 2n, which is too much. So I need to have another generator y of degree 4n minus 1, which kills x squared. Otherwise, I don't get the right answer on the level of cohomology. So I have two generators, x and y, and x lives in degree 2n, y lives in degree 4n minus 1. So even dimensional spheres have two groups, two homotopy groups, which have three components, and all other homotopy groups are torsion. And the same strategy works for Lie groups and other spaces. Basically, the answer for Lie groups. So suppose I have a Lie group. G, I take the rational cohomology I take well, the rational cohomology is a ring. no surprises there. I want to quotient by decomposable elements. Which means I take the ideal generated by decomposable elements, meaning a product of two elements of positive degree. And the result is the space. Well, the result is a graded vector space. Okay, the ith component of this vector space is pi I of G tensor Q. Well, if I want it to be factorial, I need to dualize. Does this formula make any sense? Oh, sorry. And basically, there's a similar recipe for all reasonable spaces. So the ranks of the homotopy groups are easy. Well, as opposed to torsion, which is not exactly easy. Okay. Now, there's a few. So this is application 1, application 2. Suppose we have a smooth compact simply connected manifold. Without boundary. And again, we suppose that the pi naught pi 1 is trivial, and M is sufficiently high dimensional. Then the smooth mapping class group of M has a faithful linear representation. Moreover, it has a faithful representation into GL of a finite dimensional Q vector space, and linear, finitely presented. We'll do it in a minute. Okay, linear, finitely presented, and and for what it's worth, commensurable with an arithmetic group. Okay, so let's explain what all this means. Firstly, MCG. MCG is the mapping class group. What is the mapping class group? Is the component group of the diffeomorphism group of M. In other words, we take diff plus. For some reason, people are more interested in diff plus. And we quotient out those which are isotopic to the identity. And we get something called the mapping class group, and the claim is this group is linear, finitely presented, and commensurable with an arithmetic group. Okay, so the word linear does. The word linear, basically, I've already said what it means. It means that this group has a faithful representation into GL of a finite dimensional Q vector space. And the Torelli group of M is also linear and finitely presented. For those of you who are familiar with with the mapping class groups of surfaces, what happens in the simply connected case for high dimensional spaces, manifolds, is the exact opposite of what happens for surfaces. For surfaces, it's not clear, not known whether the mapping class group is linear, an open problem. It's not known whether the Torelli group is finitely presented. People suspect the answer is no, but nobody knows, except in genus 2 when it's known to be not finitely presented, and so on. Does this make any sense? Okay. Do we want to know what commensurable with blah 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 means? Okay. So commensurable. Commensurability is an equivalence relation on groups generated by passing passing to a subgroup of finite index and the inverse. Suppose I have a group, then any subgroup of finite index is commensurable. But this subgroup of finite index may happen to be a subgroup of finite index in another group. So I can go from the larger group to a subgroup of finite index and vice versa. For example, a group is commensurable with the trivial group if and only if it's finite. With an arithmetic group. Now we want to know what an arithmetic group is. But it's complicated. Let me explain what commensurable with an arithmetic group means. So suppose I have G inside G ln Q. And suppose G is algebraic. So it's given as the set of solutions of some number of algebraic equations. Now, I can intersect G with G ln Z. And I call the result an arithmetic group. Very well, but this is awfully non-canonical. What happens if I take an arbitrary sublattice of Q to the nth? Well, I get something else instead of G ln Z. Something else meaning it's isomorphic but different from G ln Z. But the resulting groups, intersections, will be commensurable. So the commensurability class behaves better than just taking stupid intersections. So we have defined arithmetic groups in a really bad way, but it's bad, but it's short. And there are many theorems about those groups. For example, the finitely presented part comes from the arithmetic part. Okay. It's not in general at all true that finitely generated groups of G, L, and Q are finitely presented. Okay, we need to have a break. We've we've worked long enough. We need a break. But before we do, are there any questions? No questions. Good. Okay, so we'll have a break, and then we'll in the next hour we'll talk a little about Postnikov towers, which well, if it so happens that everyone knows what those are, we'll talk about something else. Дальше что работает? Да?
Запись не останавливается.
Так, 1, 2, 3. 1, 2, 3. Так, ну хорошо. Ой, так. Ой. Okay. Два. Okay, well, there's one thing which I wanted to do in the first hour, but didn't. There's a simple construction of the localized category. Let me just mention how it works and skip the details. Localizations exist. Well, the objects are the same. Well, suppose I have two objects of the localized category. How to define morphisms? Well, to begin with, we consider sequences of this type, or just like what I've written here, such that the wrong way arrows are in W. Well, all other arrows must go from the left to the right. But we introduce an equivalence relation on the set of sequences, and And this equivalence relation is generated by the following. Well, firstly, we can compose composable arrows or uncompose. Well, secondly, we are allowed to do the same with the wrong way arrows. We compose or uncompose, and we're able to compose because the class W is closed with respect to composition. Next we are allowed to insert identities and the wrong way identities, and fourth, we need another type of relations which guarantee that all arrows from W are invertible. Well, this is what it says, and here the arrow is the same. Here as well, whereas here they are not necessarily the same. W1, W2, and here W is W2 composed with W1. Okay. And this is it. Well, the sequences can be composed, and it's relatively straightforward to check that this defines a composition on the equivalence classes and the rest. Now, there's one thing which I need to add here. There is a way to topologize this construction. Namely, instead of just a set, there is a way to construct a topological space such that the components of the space will be one-to-one to the elements of the set. And this is called the hammock localization. The hammock localization is not just a category. It's a category enriched in simplicial sets, or which is more or less the same topological spaces. And this is this can be viewed as one of the incarnations of infinity one categories, which we talked about a lot last semester. Anyway, so this is just a side remark, but look at this composition. It resembles a hammock. So hence the terminology. So just localization is by naught of the hammock localization. Are there any questions? Okay, well, in this case, let's talk about something else. We will talk about general categorical nonsense if people want it. If people don't care much about category theory, we'll just talk about topology. Okay, so we will need Postnikov towers. Let's try to recall what those are. Well, first we need vibration sequences. There is a way to turn every map of topological spaces, well, sufficient and nice topological spaces, let's say CW complexes, into a self-vibration. Does the expression self-vibration make any sense? Well, let's recall how it works. So, well, to avoid unnecessary complications, let's assume that all spaces are CW complexes. Every map can be decomposed as first an equivalence followed by self-operation. In fact, this equivalence will be a co-fibration, but let's not worry about that. Say again? This is what we'll explain in a minute. So we want to construct this space and the two arrows. Let's do that. I will explain what it says on the board. Well, firstly, what is Py? It's just the space of all continuous maps from 0, 1 into Y. In other words, the space of all paths. There are two ways to map, well, infinitely many, but two preferred ways to map a path into Y. One can take the beginning, or one can take the end. Let's take the beginning. So we have this map, and we have this map. Now, the diagram is clear. What is, but except for the for this thing, I'm saying limb. Does the word limb make any sense? A comma C cross A comma C such that f of A is G of C. So my claim is limbs for spaces can be calculated in sets in Y. Well, we have the forgetful functor from spaces to sets. We take a space and forget everything. Now the question is, does this functor preserve limits or co-limits or both or neither? Well, it would preserve limits if it were to happen that that it were a right adjoint. Well, to check it's a right adjoint, we need to It would suffice to construct a left adjoint. Now, what's the left adjoint? Okay, so we have the forgetful functor top to set. Now we want this functor to be a right adjoint, so it has a left adjoint, which is what? The discrete or co-discrete? Well, it's easy enough to check. We want top. Let's call this f. We want to have top f of x, where x is in set. Why? To be the same as set x, y, where y is on top. So we want to have lots of continuous maps from f of x to y, and in order for that to be as many as possible, f of x should be what? Discrete or co-discrete? F of x should be discrete. If f of x is discrete, then basically any map from x to y is continuous, which makes the left-hand side equal the right-hand side. So the arrow here preserves limits. Why? Well, because it's a right adjoint. But it's also a left adjoint, so it does preserve co-limits as well. And the right adjoint would be the same space with co-discrete topology. Anyway, so as sets, we are allowed to the forgetful functor commutes with co-limits. So set-wise, we get the same answer as when we calculate the limit in sets. Okay, so now we understand everything in this diagram, do we? Good. Now, I have defined EF. I need to define everything else. So, well, I need to define a map. I need to define a map from X to F. And the map works as follows. Suppose I have an X, a small x inside capital X. I map it here, and then I consider the constant path with value f of x. and this is it. And then I need to define a map from EF to Y. What do I do? I take the endpoint of the component which lives in PY. And my claim, this map is this map is a self-vibration. And this is this map is a homotopy equivalence. Well, because basically every path is homotopic to the constant path relative to the starting point. And from basically by definition, we have the composition, which is F. Now I want to calculate the fiber. The fiber of this thing is the fiber of this thing is just the parameter of a point. Which point doesn't matter, any point. Up to homotopy equivalence, the result will be the same regardless of the point. Are there any questions? The fiber. Let's calculate the fiber. The CR fiber of F is the same as the fiber of EF to Y, and it's by definition the limit of the following diagram. The fiber, let's say, of EX to Y over Y in capital Y. Okay, so the diagram is very similar, but this time I have the not the space of paths, but the space of paths which start at Y or end at Y. And the map is the same. The maps are the same. F is F, and the map, the vertical one is just the beginning, the starting point. Well, let's look at this. No colored chalk. Doesn't matter. Let's look at this. What is this? Well, this is the path loop vibration. And by the way, is it clear that the preimage of small y is the limit of this diagram? Well, what's the preimage? It's the set. Set theoretically. It's the set of all x comma gamma such that gamma of 0 is f of x, gamma of 1 is y. This is by definition. Okay, well, this is exactly the same, again by definition. Are there any questions? Okay, in other words, the path loop vibration. Does this expression make any sense? Well, basically, this path loop map is written here, and the only thing one needs to check is that this map is a self vibration, and this well, this is something one can read in Hatcher's book, or basically any book on algebraic topology. Okay, so in other words, the Serre fiber is the pullback of the path loop vibration of y under F. And this is all we will need to know about the Serre fiber for today. Well, let's call it FF, which is not a particularly good way of denoting things, but I can't think of any better way offhand. So the arrow FF to X is basically the same thing. The pullback of the path loop vibration under F. So we have the path loop vibration of Y. We have a map from X to Y. We pull back, we pull the path loop vibration back. What do we get? We get the map FF to X. So the cell fiber is not just a space. It's a space which comes with a vibration into X. What's the fiber of this vibration? So in particular, FF to X is a vibration. What's the fiber of this vibration? Anyone? What's the fiber of this vibration? The fiber of this vibration is what? It's the loop space of Y. Well, when we pull back, we get the same fiber. So the fiber is the loop space of Y. So we get the following diagram. We start with F, which goes from X to Y. Well, we okay. To simplify, I will just I will not write the comparison maps. Okay, so we have we start with the map X to Y, and then we turn it into self-vibration. We get the cell fiber F. The map from F to X is already a self-vibration, so we don't need to do anything else. The fiber is omega Y, and then we take this bit, we apply omega to it, and we can continue this the sequence indefinitely to the left. And this sequence is called the vibration sequence. several things which we need, which can be said about this sequence. For example, if we take this map and take its Serre fiber, we get omega x, and this map is not just any map; it's omega of this map, and so on. So there are lots of things which can be said, but need to be proved. At the moment, we do not need any of those apart from basically this one. So we will not saying anything else about the vibration sequence, except that well, here it is, and the first bit of the sequence looks like well, this is how it looks like, and this is all we need at the moment. Are there any questions? Okay, what do we do next? Well, next we need the Postnikov towers and K invariance. Does the expression Postnikov tower make any sense? And K invariance. Let's talk about those. Okay, so we start with the space. Again, let's assume it's a CW complex to avoid unnecessary complications. And we want to construct this Postnikov tower. So the nth stage of the Postnikov tower is not just a space; it's a space equipped with a map from X and we require two things. Thing number one, the homotopy groups of Xn should vanish starting from the n plus first one. And secondly, we want that this map should induce an isomorphism of all homotopy groups of dimension less than or equal n. Okay, does the word homotopy group homotopy groups make any sense? Good. So how to construct xn. Now, the recipe is one should kill all higher homotypic groups by attaching cells of degree n+2 or greater. Does this make any sense at all? Sort of, but not really. Okay. Well, suppose I have some element of pi n+1. Well, it's represented by a map of the sphere as n+1 into x. What do? I use this map to attach an n+2 cell. Now here comes the question. Why doesn't this procedure change the lower homotypic groups? Okay, so I have Sn+1 goes to x. It's called F. I attach dn+2, and my claim is pi less than or equal n of this thing is the same as pi less than or equal n of z, of x. Why? Yes, let's use cellular approximation theorem. The n+1 skeleton of this thing is exactly the same as the n+1 skeleton of this thing. Well, let's assume the map is cellular, which we can always do if x is CW. Then the n+1 skeleton are the same, which means the homotypic groups up to the nth one are the same. Okay, so first we kill off all elements of pi n+1. Then we do the same with pi n+2, attaching cells of dimension n+3. But this time, the procedure does not affect any of the homotypic groups of dimension n+1 or lower, and so on. Does this make sense? Good. Okay, so we have sort of constructed xn. Sort of. In practice, if you take a relatively simple space such as sphere, for example, it's usually quite difficult to tell to construct the nth stage of the Bosnikov tower, especially especially if we need to kill infinitely many cells. Well, so far this construction is purely theoretical, and we will see how in rational homotopy theory everything simplifies. Anyway, so we have constructed this space, and the map is just the inclusion. Okay. Now, my next claim is that for every n, n plus 1, there exists a map from xn plus 1 to xn, which makes this diagram commute. Commutes up to homotopy. Well, basically, the spaces, all spaces xn are well defined only up to homotopy equivalence because we use cellular approximation a lot in this construction. So there is no preferred xn up to homomorphism, only up to homotopy equivalence, but it doesn't matter. Anyway, we have so the claim is this. Actually, no. Actually, there is a way to make this diagram commute on the nose if we use this construction of xn's, because x just commutes without up to homotopy, just commutes. If we use x, if we construct xn as x with some cells attached. Why? Well, suppose I have f from x to y. And suppose I attach a cell. Then the extension exists if and only if the composition f first G then F is null homotopic, which means well, basically it's 0 in the corresponding homotopy group. And then we look at the homotopy groups of Xn. They're all zeros starting from the n plus first one. And then we remember that xn plus 1 is obtained by attaching n plus 3 disks along maps of n plus 2 spheres. Well, any map of an n plus 2 sphere into Xn is 0 in the homotopy group because the homotopy group itself is 0. Does this make sense? This implies this. Okay. Now, as we've just seen, every map can be turned into a self-vibration. Good. Well, we have this map from Xn plus 1 to Xn. Let's make it a self-vibration and see what happens. Well, the claim is the self-fiber is k by n plus 1, n plus 1. Now, I've written k something something. Does this notation make any sense? Okay, so well, just in case it's a space such that the n plus first homotopy group is pi n plus 1, well, pi n plus 1 of x, and all other homotopy groups are 0 or trivial. So why do we have this? Why do I claim this? Well, it so happens that for self-vibrations we also have a long exact sequence of the homotopy groups, and this is using the sequence. This is straightforward. So we have okay. Now I want to change I want to replace n plus 1 with n and just n with n minus 1. Or because it looks nicer. But anyway, let's maybe let's not do it because it's otherwise confusing. Okay, let me keep the n plus 1 and here n pi n plus 1x n plus 1 x minus 1 etc. So we get a self-vibration of this type. Now, suppose suppose this thing can be extended to the right, so that the whole thing is still a vibration sequence. So what do we suppose? So suppose we have k by n plus 1 plus 1 xn plus 1 xn question mark such that suppose there is a homotopy commutative diagram where all vertical arrows are homotopy equivalences. The question mark is something which will, well, we don't know what it is yet, but we'll see. We'll shortly see what it is, and the bottom row suppose that there is a diagram homotopy commutative. Diagram of this form, such that the bottom row is the vibration sequence. Well, then this is something that needs to be proved. It's not for free. But, let's suppose this. Then, well, omega is k by n plus 1 n omega b. So b itself is k by n plus 1 what? N. Yes. So there is a unique way to de-loop an Eilenberg-MacLane space. Same as there is a unique way to desuspend a sphere. Although, again, here we assume that n is greater than, 1 or 2, and same for spheres. In general, de-looping is non-unique, desuspending is non-unique, but the first one is unique for Eilenberg-MacLanes, and the second one is unique for spheres and for Moore spaces. Okay. Okay. So what do we get? We get two things. So firstly, xn plus 1 to xn is the pullback of the path loop vibration of k by n plus 1 n under xn to k by n plus 1 n. Does this make any sense? Okay, so now we are ready to define the k invariants. Well, let's recall the following thing. Well, this is something which we've just talked about when we talked about the cell fibers. So we have a vibration from xn to k by n plus 1, comma n. So the question mark is the same as b, and it's the same as k by n plus 1 n. And then xn plus 1 becomes the cell fiber. And we already know what what the map from the cell fiber to xn is. It's just the pullback of the path loop vibration of the question mark, which is k by n plus 1 n, under this map. Let's recall the following thing. Homotopy classes of maps from x to k by n are the same, or Eilenberg-MacLane spaces represent cohomology. What does this mean? Well, this is what it means. The homotopy classes of maps into k by n as a functor. K by n is a double loop space, so this functor naturally lifts to a billion groups. And this functor is isomorphic to this functor. Again, this is something that can be found in many books on algebraic topology. This is in Hatcher, Fuchs and Fomenko, and the rest of them. Okay, so in particular, we have a very distinguished class which corresponds to x equal identity, and the map, x equal, sorry, okay, so hn k pi comma n comma pi. So we can take x equal k pi n and the map to be identity. This gives us some cohomology class. Well, this class is usually denoted iota, and it's called the fundamental class. The fundamental class of what? Of k pi n. Very well. So the nth k-invariant of x is the pullback of iota under the map xn to k by n plus 1 n. Did I mess up the okay, so iota lives in so this k-invariant will live in H n plus 1 of xn sorry, I've messed up the n's and n plus 1s. Once again, the fundamental class. So we have a map from xn to k pi n plus 1 n. Is this correct? Well, yes, I think so. So we have this map. So we yes, we have hn x hn xn by n plus 1. Something is wrong here. so let's look at this again. The loop space when we the loop space just de-looping lowers the n. And we have a map from xn to да, там где-то я пропустил, значит, то есть здесь n плюс 2. Так, okay, that's a good remark. Let's see. So omega k pi n. Omega k pi n. No, k pi n is omega k pi n plus 1. Is this correct? Let's check. Well, we use the path loop fibration. We have the space of paths, which is a point. It's fibered over k pi n, and the fiber is omega k pi n. So the okay, well, let's check it. So we have well, let's check it. So we have pi n k pi n, which is pi, and it's the base, and we omega k pi n. Okay, so the base is isomorphic to the fiber, so the omega k pi n is k pi n minus 1. So omega k pi n plus 1 is k pi n. Did I mess it up again or not? If I want to put an omega, I need to put a plus 1. When I do-loop, I get n plus 2. What does this change? This changes only one thing. I need to replace n by n plus 2. Good. So the nth k invariant confusingly lives in the n plus second cohomology of xn with coefficients in pi n plus 1. I messed unless I messed up the indices again. Okay, so the collection of all k invariants determine x up to homotop equivalent. So it's a very strong invariant. It's a complete invariant of x, at least in the simply connected case. But integrally, it's not so easy to calculate those invariants, whereas rationally, it's much easier. And this is what we'll talk about next time. And basically, starting from those k invariants, we will be able to at least construct a minimal model of a simply connected space. Are there any questions? Okay, good. Then this is it, and